Hello students, welcome to Vista's Learning. This is Shruti D. Nadiga. We are in 11th standard chemistry and I'm your chemistry tutor. We Vista's Learning provide you a very good education for a very less amount, and we are struggling to reach this quality education for all. Hope you all have seen our videos. If you have any of the doubts, students, you can get back to us. And if you have missed any of the videos, you can browse into our web application www.v-learning.in. Fine, we'll get into our syllabus now. What we are doing today, can you guess what it is? Yes, it's a part of periodic table, right? This is the rightmost part of the periodic table. And we have only 6 groups here, which we call it as P block elements. And today we are getting into the next chapter, that is P block elements. This is around 11th chapter, right? We have already finished our 10th chapter, that is S block elements. What will we learn about these elements, students? We'll learn how they have been grouped and what are their properties, either chemical as well as physical properties we are learning with their uses. Same thing in P block elements also. Here in this chapter we are learning about each group and how many groups are there, what are their chemical and physical properties with their some of the compounds and uses. Got it? So this is our lecturing class 1 with P block elements. Fine, you can see here we have the periodic table, and here rightmost we have the P block elements. In this, except helium, we have all other groups which is been called as non-metals over there. We also have metals, non-metals and metalloids in this group. How we get to know about this P block elements? If you see, here, as we have 6 groups, for each group we have different chemical properties. They are depending on the valencies. So we know that in p orbital we have 3 suborbitals, where each suborbital will have 2 electrons each. So px, py and pz respectively. So by that we understand 6 electrons are getting into the p orbital. So we have 6 groups accordingly. If the 1 electron is getting into the p block for px orbital, that comes under 13 group. If it is 2 electrons, it goes to the py of p orbital, py suborbital of p orbital, that gives 14. Likewise, we have 15, 16, 17, 18, and it depends on valence electrons which is entering into the p block or p orbitals, forming the P block elements. Now we have the points which we need to know, the basic points about this P block elements. How many groups are there in P block elements? According to the p orbital, how many electrons are entering into the outermost orbital or valence electrons which is entering into the p orbital? It will be from 1 to 6. So it depends on that, those electrons we get the group. So p orbital can hold 6 electrons, and hence we have 6 p block elements starting from 13 to 18. And we have boron, carbon, nitrogen, oxygen, fluorine and helium heading the group. Means they are the first members of the group, and their valence electronic configuration will be ns2 np 1 to 6. That means this ns2 is common, because in the outermost shell s orbital will be filled. If the outermost electron is entering into the s orbital, then it will come to the s block element. Whereas here the electrons which are entering into the p orbital will be grouped under p block elements. So already they will be having s block which is completely filled. And the next electron to the outermost shell which is going to the p orbital will be grouped under p block elements, and we get 1 ns2 np 1 to 6. 1 to 6 means the p orbital will be having 3 suborbital. If it is having 1 electron entering into the p orbital, it will go to the 13th group. If it is having 2, it goes to 14. This will be in 15, 16, 17 and 18 respectively. Got it? Next, the inner core of the electronic configuration may differ. Obviously true, because as the outermost orbit can be of ns2 np1 to 6. The core orbitals might be anything. It depends on the which period they are, right? If they are in first period, they will be having only 1 orbital. You need to remember, in first period, we have only 2 elements, that is hydrogen and helium. Helium don't have p orbital, but still it is in the p block elements according to its chemical properties, as it is coming with the noble gases. Got it? So now the core electrons obviously differ, and the maximum oxidation state shown by the p block elements is equal to the total number of valence electrons present. Why we are using total number? That means the electrons present in s orbital plus electron present in p orbital. The total electrons in the outermost shell will give you the maximum oxidation state. If the electron is 1 in p orbital, then the element can have 2, like s2, ns2, np1. So 2 plus 1. So totally 3 electronic configuration, like 3 electrons are there in the outermost shell. So we can have 3 electrons to be removed, and hence we get the maximum oxidation state here as 2 plus 1, 3. Next point is that we have the electronic configuration. Which electronic configuration? Valence shell electronic configuration of all the different groups from 13 to 16 here. So 18 here. So we can see the first one, 13 group elements. It will be having 3 electrons. Why it will be having 3 electrons? Because s orbital will have 2, p will have 1. 2 plus 1 is 3. So we have 3 valence electrons in 13 group elements, and its electronic configuration will be ns2 np1. Why we are taking n here? What does the n represent here? N means if we are taking the period, the first period will have s2, 1s2, 1p1. Is it possible, students? I have already told you in first period we don't have p orbital, so this cannot be possible. Only will be having 1s2. But will be having second period 2s2, 2p1. Got it? P orbital will be there for only from second shell or second orbit, not for first one. Got it? The first one will have only s orbit. There is no orbital. There is no p orbital in first shell or first orbit. So there is no 1p. That always starts with 2p. Okay. So we have 2s2, 2p1. Likewise, it will be 3s2, 3p1, 4s2, 4p1. For down the group, what happens? This n will be from 2 to 6 or 7. Okay. Next one is that group 14, where in group 14 we have 4 valence electrons, and the orbital will have the valency of 4 with ns2, np2 as a electronic configuration. Next we have 5 for group 15. So valence shell will have 5 electrons, 5 valence electrons. How? ns2, np3. Got it? And next 16th one will be having 6 valence electrons and ns2, np4, 4 plus 2, 6. Got it? So next we have for group 17, 7 valence electrons. So Ns2, Np5. The next is the last one where we have group 18 with 8 valence electrons and we have Ns2, Np6. Here what you can easily understand is that students, for 13th group you will be having 3 valency. 14th 4, 15th 5, 16th 6, 17th 7, 18 8 valence electrons. So you can easily remember this. Okay, if we give you the group number, you can easily find out what is its valency or valence electrons. Got it? If I ask you what's the valence electrons in group 15, you can easily say it's 5. In group 17, it's 7. That means 7 electrons are present in group 17 elements in the outermost shell. Got it? Next. So in boron, carbon and nitrogen families, the oxidation group or the group oxidation state is the most stable state for the lighter elements in the group. That means in boron, carbon and nitrogen, we have the 13, 14 and 15th group. In all these 3 groups, the first element is boron, next carbon, next nitrogen. What this point is saying is that all these lighter elements we know down the group, the size increases. As the size increases, the elements become heavier, right? So these elements will have the most stable state than other elements in the same group. Oxidation state 2 units less than that of the group oxidation state becomes progressively more stable for the heavier elements. That means if I have the elements which are heavier, that means down the group the size increases. As size increases, it will be heavier, right? So what happens to these heavy elements is that they will not generally get the valence or oxidation state as we calculated. For example, the first element, if I take the boron family, down the group, the last one if you take, what happens? It will be more heavy, okay? So when it is being more heavy, it will be having Ns2, Np1, right? It can easily lose this 1 electron and this 2 electrons it cannot, because it is inert pair effect. Due to inert pair effect means it will be always s orbital will have 2 electrons. So it will be always paired. When it is paired, it is not so easy to remove it. So we need more energy to remove it, whereas the higher or heavier elements will not give much energy to lose the electrons, not take the electrons. So what happens for the heavier elements? The oxidation state will be 2 units less than the lighter one. Got it? So for boron, we can say it will be 3. For the heavier metals in the boron family, it might be 1. So occurrence of the oxidation states of 2 units less than the group oxidation states are sometimes attributed to the inert pair effect. That is what I just said. You will be having the s orbital and it will be paired. So pair effect, inert means they are not like reacting or responding. So we need to give more energy for that. That effect will be called as inert pair effect. Next point is that it is interesting to know that the non-metals and metalloids exist only in the p block elements. We see that s block is completely made up of metals, right? Except hydrogen. But here in p block elements, other than this p block elements, you cannot find metalloids and non-metals in any other blocks, either s block, nor in the p block, d block, nor in the f block. We just see these metals, non-metals and the metalloids in p block alone. Got it? You can see over here, the rightmost part is the p block elements except helium, because it is having 1s2, it doesn't have p orbital, and except them we have these groups starting from 13 to 18, where we have boron, carbon, nitrogen, oxygen, fluorine and helium families. The boron will be having these three, and we'll take the 13 group elements and check out with the studies of 13 group elements. As we know, in 13 group elements, we have 3 electrons in the outermost shell, and the size will be like this. Down the group, as we know, size increases, but the core elements or the electrons will increase, right? They differ in core, inner core electrons, and that makes the effective physical properties. They affect the physical properties like atomic radius, ionic radius and ionization energy, with also some of the chemical properties. So hope you understand this. Due to the increase in size, the core electrons will differ. It differs from boron to thallium. So what happens? It differs. You can see the crowding is more down the group. When the shielding effect will be increased. So when shielding effect increases, obviously the physical and chemical properties in the same group will differ. What are the some of the physical properties? Like radius will increase. Yes, obviously they have the difference in the atomic radius. We have ionic radius, means when they react with other elements, either they donate the electron or take the electron, right? At that time what happens? Ions have been formed. So while forming the ions, the ionic radius also differs with boron to the thallium, and we have ionization energy, which also matters here. Down the group, ionization energy, what happens? We have studied in S block, right? So here they can easily lose the electrons. So ionization energy decreases down the group. And we have some of the chemical properties based on this ionization enthalpy or energy will be having the reaction. So some will react soon, some will not. We'll just study them. The non-metallic character of elements decreases down the group. As we say here, the non-metals, the first groups are most non-metals. So we see here, we'll get the boron, carbon, nitrogen. They are the metallic, non-metallic in nature, fluorine and all. When we come down, they convert or they change or they decreases their metallic properties to non-metallic properties to metallic properties. So that is what, if we have fluorine here, we have iodine here, down the group, what happens? Fluorine, chlorine, bromine, acetate. So down the group, what happens? We have, down the group, we have decrease in metallic, non-metallic property, where fluorine is highly non-metallic, and this iodine, if we consider just the halogens, the iodine is less non-metallic in nature. Next, the heaviest element in the p block elements is in the metallic nature. That will be exhibiting the metallic nature, and this change from non-metallic to the metallic character brings diversity in the chemistry of these elements in p block elements. Non-metals have higher ionization enthalpy. Non-metals have higher ionization enthalpy. That means they cannot lose the electrons easily. Ionization enthalpy means energy required to take out the outermost electron, right? So here, when non-metals are having 6 or 7 electrons in the outermost shell, they cannot easily lose these electrons. Instead, they can easily gain 1 or 2 electrons. Listen, to gain 1 or 2 electron, you require some energy. To lose electron, you require some energy. But here, when you are comparing 1 electron you want to gain, or you have to lose 7 electrons to get the stability. Which is better? To gain 1 electron is better, right? Or if you have 6 electrons and you need to gain only 2 electrons, is it better to gain 2 electrons or lose 6 electrons? Anyway, energy will be lost. For one electron, if we are using some amount of energy, then 6 times we have to lose it. Here only 2 times. Which is better? Better to take the 2 electrons. So here non-metals will not easily lose the electrons. If they have to lose the electrons, you have to give more energy for them. Why? Because generally non-metals will have smaller size compared to the metals. Got it? Yes. And their effective nuclear charge also matters. So non-metals have higher ionization enthalpy and higher electron negativities than that of metals. So here we have a metal which is having high ionization energy and high electronic negativity with non-metals, whereas for metals we have low ionization energy, low electronegativity, and when they lose the electrons, if we see here, when metals are there, we'll be having only 1 electron in the outermost shell. So what happens? You can easily lose the electrons and they become positively charged particles, whereas non-metals will gain the electron due to the high electronegativity, and they become negatively charged particle. We call negatively charged particle as anions. So here that metals and non-metals, both when they lose the electron, the other gains the electron, they get positive and negative charge, they combine together. You can see the electronegativities. This is 0.9, whereas that is 3. So chlorine is having very high electronegativity, so it can easily gain the electron from sodium. So what matters here? It is positively charged particle, it is negatively charged particle by giving the electrons. If we see the non-metal and non-metal, when they combine together, they have the sharing of electrons, which we call it as covalent bond. The donating the electron comes as the ionic bond, where this is called as a covalent bond. You can see that one non-metallic element atom on the other non-metallic atom will combine together with sharing of electrons. So if you see, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons now in one of this, whereas here 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons both, but before it was just 7 electron each. That means this is the halogen which is having 2, 8, 8. So we have 2, 8, 7. So 17 is chlorine. So if you take the chlorine atom, it will be having 7 electrons in the outermost shell. So each chlorine atom share 1 electron each. So this is from this is from there, the other chlorine atom. So they share the electron to get the octet structure, and now they will be stable. So this bond between non-metal and non-metal will be a covalent bond. Whereas previously what we saw, when we have this metal and non-metal combined together to give you a ions, right? Positive charge and negative charge, because transfer of electrons takes place. This we call it as ionic bond. It depends on the negativity. One which is having higher electronegativity will gain the electron from the one which is having lower electronegativity and forms a positive and negative charge, and hence this is a ionic bond between metal and a non-metal. Whereas we have metal and non-metal which is combining by sharing of electrons, which leads to the covalent bond. Did you understand this, students? Good. So in contrast to metals which readily form cations, non-metals readily form anions. That means they can easily lose the electrons. The non-metal oxides are acidic or neutral, whereas the metal oxides are basic in nature. That means if we speak about the oxides, so we know that lithium, sodium oxides, right? If we go with this, we can go ahead with peroxide or superoxides. or oxides. So if we take the metallic oxide, that will be basic in nature. If I consider the non-metallic oxides, for example, carbon dioxide. So carbon dioxide is acidic in nature, whereas if I take carbon monoxide, that will be neutral. So we have neutral, acidic and metallic, like basic oxides. The metals reacting with oxygen, non-metals reacting with oxygen. When metals react with oxygen, we get the basic oxides. Where non-metals are reacting with oxygen, we get the acidic oxide or neutral oxides. The first members of P block differs from the remaining. Why? Because they will be having a small size, and with that they will not have the d orbital in their for example, if we are going ahead with first period, second period, third period, I am just considering these three. First period will have only s orbital, second period will have only s and p orbital, third period will have s and p with d orbital. Either the electrons are there or not, that doesn't matter. If they have the empty orbital also, they can take them in hybridization. But for second period, we don't have d orbital here. So since there is no d orbital, we cannot extend the oxidation states, right? So the first members of P block differs from the other elements or other periods. You can also say that as other members in the same group. What are the two major respects that we have that differ from first elements or first members of each group? The first thing is that size. As I said, the size matters, and all other properties which depend on size. We know that down the group size increases, across the period size decreases, and that is the most important thing which differs their properties. And hence, as we know, the first aspect is size. The size makes the other properties differ, and the lightest P block elements show same kind of differences as the lightest S block elements like lithium and beryllium. As we know that they will be also having we studied about how the beryllium and lithium differ from the other elements, right? Because they are in the first members of the S block elements, and hence they differ from other elements due to the size effect. Same thing happens with the P block elements. The first members will be very small than that of the other elements, and that size differs the properties of those first elements in each group. The second important difference which applies only to the P block elements arises the effect of d orbitals. So they don't have the d orbitals in the valence shell, whereas the heavier elements have the d orbital in the valence shell. So they lack this in second period, means d block orbitals or d orbitals are lacking in the second period, and hence as we are starting with the second period, those elements will not have this d orbital in them, and hence that makes the difference in the P block elements. So first members of all the P orbitals, like P block elements. The second period elements of P orbital starts from boron are restricted to the maximum covalency of 4. Means boron, if you take, that will be having 2 electrons in the s orbital, and if you take the p orbital, it will be having 2 electrons, right? So here what happens, you will have only 1 electron here. So the first fine. So first s orbital will be filled, and then p orbital it occupies singly, and then pairs up, right? So we have this. So maximum this boron can have 4 valency or covalency. How they can say 4? We have only 3 electrons. It depends on the orbitals which are available. So when here we have 2s2, 2p1, we have 3 suborbitals and here 1 plus 4. So totally 4 suborbitals for boron. So we can have maximum of only 4 covalency. But if you see for other elements, heavier elements, we also have d orbital there. So this 5 also adds up and they can have 5 plus 4, 9 as a covalency, but it is not possible to have 9 covalency as we have only 8 electrons in the outermost orbital. The third period elements of P group with the electronic configuration 3s2, 3np means the third group period. In the third period, whatever it is, either it is in 13, 14, 15, 16, 17 or 18, any groups that will be having this configuration 3s2, 3pn, right? If it is 1, it comes to the 13 group. 14 group, if it is pn is 2. When n is 2, it comes to 14. Likewise, it goes on. So here we are speaking about third period. So in third period, we have the vacant 3d orbital. We have 3d orbital. That means in third period, we will be having s, p and d orbitals, where d orbital don't have any electrons, but it is empty. So that we call it as, we have vacant 3d orbitals lying between the 3p and 4s levels, and that we use it for expanding our oxidation state. So using these d orbital, third period elements can expand their covalency from 4 to above. Okay, while boron forms only Bf4 minus, means it can have 3 electrons. One more electron means it is gaining from fluorine, so it will be having negative sign here. This is a complexes we will study in detail further. If you see here, boron can combine with 4 fluorine atom. Okay, and it forms negatively charged particle here. Okay, whereas aluminium can have, it will be having 6 fluorine which is bond with aluminium. Why? Because aluminium will have d orbitals, so they can expand. So we have AlF6 3 minus ion, where they both are of same family, boron, and then we have aluminium. Even though it is the third, it is the second and this is the third period, it is having a very small difference, but still this is having 3d orbital, where the d orbital is absent here. Due to that, boron can have only 4 fluorine atom which is been combining with boron. That means it can only have 4 covalency, where aluminium can expand its covalency to 6 AlF6. The combined effect of size and availability of d orbitals considerably influences the ability of these elements to form pi bonds. Pi bonds is, they are laterally overlapping. Okay, this forms to the pi bond. That means double bonds or multiple bonds will be formed due to this pi bonds. Pi bonds cannot be existed alone. If you have single bond between any of the elements, then that will be the sigma bond. If you have 2, then it will be 1 pi bond. If you have 3, then it will be 2 pi bonds. 1 sigma should be there with which is accompanying pi bond. There is no only sigma bond, only pi bond which is exhibiting. If you have single bond, that will be always sigma bond. Okay. If you have sigma bond, then only you can have pi bond. The first member of a group differs from the heavier members in its ability to form p pi multiple bonds. Means we have p orbitals which are forming the pi bond, that is given by p pi. If we have d orbital and they are forming the pi bond, we call it as d pi bond. Okay, since it is p orbital, we call it as p orbitals are overlapping laterally, so we have p pi multiple bond. Why we call multiple bond? Because more than one if you have, we call it as double bond or triple bond, so that will be called as a multiple bond. Got it? So here, apart from the first member, all others have the ability to form this p pi multiple bonds, and it can form with itself. For example, as I said, carbon, so it can form by itself and to the other second row elements also. So here we have these p orbitals where we can see p block elements with all the groups from 13, 14, 15. We have boron, carbon, nitrogen, oxygen, fluorine and helium which are leading them. Down the group, all the elements in the p orbital will be having, down the group, size increases. So you can see all the first member will be having smaller size. So that makes the differs in physical and chemical properties of other. If you take the second period, as we see, we can have only 4 boron with the 4 fluorine with the boron atom. That means only 4 valency can be formed with boron. Whereas in third period elements, we can have expansion due to presence of d orbital, and hence we have the aluminium forming hexafluoride ion. Got this? Any doubt over here? Good. The next point is that this type of pi bonding is not particularly strong for the heavier p orbital or p block elements. Means if it is going down, if you have the larger orbital, they cannot easily have the control on the outermost orbital. So this expansion or pp bonding, the pi bonding cannot be easy for the heavier, completely heavier elements in the same group. The higher or heavier elements do form pi bond, but this involves d orbital. So we'll be having d pi orbital. So you can see here d orbital, this is d lobe, this is p lobe, and they overlap. That can also be done d pi, p pi, or dd orbitals can overlap and we get d pi orbital. So that will be done with the heavier elements. The coordination number in species of heavier elements may be higher than for the first elements in the same oxidation state. That means for first elements of the same group will be having lesser oxidation states, where when we go down it will be more. The coordination number, okay. We study this in the next year in coordination chemistry. We'll study in detail what is this complexes of coordination complexes, what is coordination compounds, we'll study in detail. So for example, if you see here +5 oxidation state for N and P, you can see here both N and P forms oxo anions. So you can have an example of this NO3 minus, where 3 coordination with pi bonding involves 1 nitrogen with p orbital. Whereas if you take the phosphite, we can see PO phosphate, PO4 minus. So 4 coordination numbers will be there, where it will be involving S, P and D orbitals contributing the pi bond. Means first we have nitrogen, then comes the phosphorus. For nitrogen we don't have d orbital. For phosphorus we have d orbital. So they can extend the D orbital with forming the pi bond. Got it? So here we have this multiple bonds which is been involved. You can see here when they are overlapping, then this is the pi bond when they overlap and form it. This is DD orbitals where they can overlap forming the d pi orbital. So this is the d pi orbital which has been formed. So you can see here the coordination number, higher coordination can be achieved from these orbitals. Next we have the boron. In the universe we can have by mass 0.001% of it, and we have, it is a typical non-metal which is hard, black in color, and it's a solid. You can see its particles, it's crystalline in nature. We have two types of boron, that is the boron powder where alpha and beta boron will be having. So they are the allotropes of boron. We have crystalline boron with alpha boron. Next, coming with the study of this boron, we'll know much more things about boron. So group 13 elements will be having the first member as boron, and we call it as boron family. Complete 13 group elements can be called as boron family, as that group is led by boron. So boron is a typical non-metal and aluminium is a metal, but also many chemical similarities are there in between boron and also aluminium. And gallium, if you see gallium, indium and thallium, nihonium are almost exclusively metallic in character. In boron family, we have boron as a non-metal, whereas aluminium will be called as amphoteric, means it will be having metallic as well as slightly non-metallic character, where the gallium to nihonium, if you see, they all are metals, purely metals. Boron is a fairly rare element. It is found rarely in the universe. Mainly occurs in orthoboric, as you can see H3BO3. That is the acid which we call it as orthoboric acid. We have borax, Na2B4O7.10H2O. We use this borax for cleaning purposes in our routine life. So we also have kernite, which is a ore. We can say that we get the boron from this ore, Na2B4O7.4H2O. What do you understand by this H2O, guys? That means this is decahydrated, this is aqua hydrated. The abundance of boron in earth crust is less than 0.0001% by mass. So there are two isotopic forms of boron, as I said. We have the crystalline one and other is alpha one. So you can have that 10B 19%, where 11B is 81%. Means they just give the number like that with the isotopic form. We know isotopes differs with the mass, right? Atomic mass. So atomic mass which is having 10 and which is having 11. 10 is having the boron which is having the atomic mass as 10 will have 19%, whereas we can find the atomic mass which is having 11 or isotope 11 will be having 81%. Boron compounds, as we said, these are the three boron compounds: orthoboric acid, kernite and borax. So borax, it is very much important in our life. As I said, we use this in our daily life, and these are the places where we find it. Next, aluminium is the most abundant metal. Aluminium is the most abundant metal and the third most abundant element in the earth crust. So we can find 8.3% by mass, and we have the oxygen which is having 45.5%. After oxygen, the next one is this aluminium, and the silicon will be having 27.7%. Borax or bauxite is the ore of aluminium, where we get aluminium from this ore, Al2O3.2H2O. It is dihydrated salt, aluminium oxide, or you can also say it as oxide, which is having the dihydrate. And we have cryolite, which is having Na3Al(F6). So they are the important minerals of aluminium. We can also say they are the important ores of aluminium. From them itself we extract the aluminium. Gallium to thallium are the, if you see gallium, indium and thallium, they are less abundant elements which are found in very less amount. So neonium has the symbol as NH. Its atomic number is 113 and atomic mass is 286 grams per mole, and the electronic configuration will be Rn is radon with 5F14, 6D10, 7S2, 7P2. So this is the configuration of neonium. So you can see outermost orbit, it will be having 2 plus 2, that is 4 electrons in the outermost shell. Neonium is a synthetically prepared radioactive element. It is a radioactive element. So next, coming with the aluminium, after boron we have the aluminium, where we are seeing aluminium is also found in the earth crust. The third one, we have the bauxite, cryolite, and you can see the formulas. It is important. We have mica, which all the 3 ores we get the aluminium. So you remember this, students, these are important for 1 mark question, even for your NEET exam, set exam, like a KSET exam and all, the entrance exams, they will be asking this formula. Electronic configuration. The outer electronic configuration of these elements is Ns2, Np1, as we know, as it is the 13 group elements. So neonium we saw it is Ns2, S2 and P2, no, it should be P1, okay, because it is in 13 group elements. You just correct it. The outermost electronic configuration is S2P1. As we said, it is in 13 group elements. It should have 3 valence electrons, and hence the electronic configuration. Okay. So a close look at to the electronic configuration suggests that while boron and aluminium have noble gas core, means they have the noble gas core, where gallium, indium have noble gas plus 10d electrons, and thallium has the noble gas plus 14f electrons plus 10d electron cores. Means inside the electrons will be having, this is not, don't get confused. What they are about to say is that when you come with the boron, aluminium, and next gallium, thallium, and then we have indium here, and then thallium. If you see all these things, when we go down the group, what happens? Size increases. So for boron, we'll be having noble gas core, like it will be having 8 electrons in the outermost, like inner shell. If you have the outermost shell with 3 electrons, exactly into that we have 8 electrons. So that gives you the noble gas core, where for gallium, indium will be having D orbitals there with this 8 electrons, we have d orbital, means 18 electrons will be there in the inner shell of the outer shell. The second most shell, we call it as ultimate shell. The next one is penultimate shell. So the second electron before the outermost shell will be called as penultimate shell. The electrons present in that penultimate shell will be having 8 electrons in boron and aluminium. Then we call it as noble gas core, because noble gas will have 8 electrons in the outermost shell. Whereas if it is having noble gas configuration plus 10 electrons, that means totally 18 electrons, that will be for gallium and indium. So for gallium and indium will be having 18 electrons. So here we are speaking about, so here we have boron, so boron, which will be having 8 electrons in the penultimate shell, and aluminium also will have 8 electrons in the penultimate shell, and then we have the gallium, which will be having 8 plus 10 electrons. Why 8 plus 10 electrons? That is, d orbital will also be present inside that. So we'll be having 18 electrons with gallium and indium. So totally 18 electrons in penultimate shell, and then we'll be having, for thallium, will be having 18, means 8 plus 10 plus 14. So totally how much it is? 22 electrons in the penultimate shell. Did you understand what is penultimate shell? The outermost shell we call it as valence shell or ultimate shell, means at the last shell, and inside that we call it as anti-penultimate shell. Okay, we call it as penultimate shell, and before that we'll call it as core. Whatever we get inside, we call it as core electrons. So this ultimate shell and this is the penultimate shell. In the second most outermost orbit will be having 8 electrons in boron and aluminium, will be having for 18 electrons for gallium and indium, and for thallium will be having totally 22 electrons. That is what the meaning of this point is. Hope you understand this, students. Good. The electronic structures of these elements are more complex than for the first two groups of the elements. When you see this, we have the first two groups as S and P block, right? Apart from that, if you see the electronic structures, these are a bit different. So physical properties, if we are speaking about 13 group elements, we have this atomic size, which is differing, you can say, down the group. It differs. It comes from 0.88 angstrom to 1.71 angstrom. If you see the gallium and aluminium, gallium is a bit less than that of the aluminium, right? Why? Because we have the electronic configuration with the d orbital. When you have the inner d orbital, they shield the electrons and attraction will be more there. So what happens? They come closer to the electron. We have the effective nuclear charge which increases and they come a bit closer to the nucleus. So the size gets decreased. Why we get this effect? Because the number of protons or nucleons also changes, and the protons will attract the outermost orbit more easily than that of aluminium. So what happens? The same orbit will be attracted more due to more number of electrons. If you see here, we have so the size between aluminium and gallium we are speaking, the size decreases. Okay, why the size decreases? Because we have effective nuclear charge, which is more for gallium. Why? Because for aluminium we don't have d orbital. For gallium we have d orbital, and that d orbital will have 10 electrons more. That means the 10 protons are more than that of aluminium. So you can see the 10 electrons are more means the 10 protons will be more in gallium. So these 10 protons will attract these electrons. The third shell will be more 10 times more attracted than that of aluminium. So what happens? Due to this presence of d orbital, they are fully filled d orbital. So 10 electrons will be more, and that will make the size decrease. The atomic radius, as we are speaking, gallium is less than that of aluminium, and this can be understood from the variation in the inner core of the electronic configuration, as the 10 electrons differs from aluminium to gallium. We have this difference, and the atomic radius of gallium is 135 picometer. You can get this in picometer or else in angstroms. So now in the textbook, as it is been given in picometer, I just want to inform you in picometer. So it is in 135 picometer, which is less than that of aluminium, which is having 143 picometer. Coming with the ionization enthalpy. Ionization enthalpy values are expected from the general trends do not decrease smoothly down the group. As we know, it depends on size, right? So from down the group, if the sizes keep on increasing, then what happens? We can easily say, yeah, down the group size increases, so ionization enthalpy decreases. But here the size decreases till aluminium, and from there increases till aluminium. From boron to aluminium it increases. From aluminium to gallium it increases, right? Like it decreases, the size decreases. So size is increasing from boron to aluminium, and it is decreasing from aluminium to gallium. So what happens? It is not just a one stretch. It is decreasing. We cannot say it is increasing. We cannot say. So it is not running smoothly, right? So we need to know how does this change. Just a while. So the decrease of boron to aluminium is associated with the increase in size, and the observed discontinuity in the ionization enthalpy values between aluminium and gallium and between indium and thallium. Why? Because here 14 electrons will be exactly more than indium to thallium. As we know, the electronic configuration, as we say, so if I just take this, we have boron, aluminium, gallium, indium, thallium, and the last one, it's okay, fine, we'll just go with this. So here we have noble gas electronic configuration till here 8. From here it will be 18, where again from here it will be 18 plus 14, right? So as from here exactly 10 electrons are more. So 10 times the attraction will be more and size decreases. Where you see here it is 14 electrons more and attraction will be more, and 14 times it decreases. It tends to decrease its size. So due to this we have difference in the ionization enthalpy. So from boron to aluminium it is down the group, ionization enthalpy increases. But when we observe from aluminium to gallium and indium to thallium, we have the difference there. It is not exactly increasing size, and so it is not the decrease in ionization enthalpy. That is due to inability of d and f electrons, presence of d orbital in gallium and f orbital in thallium. We have this difference which have low screening effect, That means they have more electrons and the screening will be less, means the shielding will be less. So the size will be a bit decreased, not increased. So to compensate the increase in the nuclear charge, they come closer. So the order of ionization enthalpies as expected is H1, that is the enthalpy, ionization enthalpy. We can just represent it like that. The sum of the first three ionization enthalpies for each element is very high. It is not easy to give the first three elements. Rest of the members are soft metals with low melting points and high electrical conductivity. We are speaking about other than boron, all other members, they are all metals. As they are soft metals, they will be having low melting point. They have the low melting point and also they have high electric conductivity. It is worthwhile to know that the gallium with unusual low melting point, we have 303 Kelvin for gallium, because gallium can exist in liquid form in 32 degrees. So we can also say at 303 Kelvin, this gallium will be having its melting point. Okay, it exists in liquid state during summer. Why? Because summer will have more than 33-34 degrees Celsius, right? So we'll be having this in liquid form or liquid state in summer. Its high boiling point 2676 Kelvin makes it useful material for measuring high temperatures. So density of the metals or elements increases down the group from boron to thallium. Obviously density increases as the addition of electron is also increasing. So electron negativity. We know that down the group what happens? Electron negativity first decreases from boron to aluminium. Yes, electron negativity decreases as size increases. Okay. Then increases marginally. It depends how the size increases or decreases. Electronegativity also depends on that with effective nuclear charge. Because as we know, we have discrepancy of this atomic size of the elements. It is not exactly the same. It is not exactly increasing or decreasing. We have differences in that, right? Due to that, what happens? It decreases, then increases, decreases and then increases. So we have this difference. So next, coming back with the physical properties. Boron is non-metallic in nature. We know that. We are just speaking about this boron now. It is extremely hard and black colored solid, as we just saw in the previous video. It exists in many allotropic forms. Mainly, we have this lattice, strong crystalline lattice. Due to that, what happens? It can form the isotopes or it can form the allotropes. We have boron has unusually high melting point. So it's a solid, hard solid. It is having high melting point and it has the allotropes. So by this, we finishes the study of P block elements. So hope you understood the students. If you have any doubts, you can get back to us. We Vista's Learning are here to help you out with your studies. If you have any doubts, you can get back to us. Thanks for watching Vista's Learning.